Now let's do a few more examples just to reinforce those ideas. So let's do an example of a cosine, graphing a cosine, which is pretty much the same, just we got to recognize, okay, this is now going to be a cosine function, not a sine. It's going to start at the top rather than at the middle. And so we have a couple numbers that we got to pay attention to how those transformations will affect the graph. So in this example, let's basically what I recommend doing, start by finding the amplitude and the period, because those are vitally important parts of the wave. So the amplitude is going to be 2a, and then the period is going to always be 2 pi divided by the number on the inside. So since that's a fraction in this case, 2 pi over k, that would be 2 pi divided by 1/2. Well, by flip and multiply, that should be 2 pi times 2 over 1, or 2 pi times 2, aka 4 pi. And again, that will tell us, well, if I'm trying to graph this wave, what's its period? That's going to be the distance it takes to finish one cycle. And if I'm trying to just graph one, that's what we need to know. So cosine will take, this wave will take 4 pi to get back to the equilibrium. Now, also I would graph the amplitude, which is 2. So it's going to go down to -2 and up to 2 instead. And otherwise, now it's a cosine wave. It's positive, so it's going to start at the top because that's where cosine starts. And again, what I would recommend is putting out my other outlining points. In this point, it would be pi, 2 pi, 3 pi. But it will have the same properties where intercepts at a quarter of the way, goes back down to min at that point, back to equilibrium 3/4 of the way, and hits max at the end. And this is a little bit, again, we're sketching it here. We're not using graph paper or anything. And that was the goal of these, is not to graph them super well, which we could do if we had the time and patience. But anyways, also one thing that we could also imagine is that with the amplitude, the wave should be vibrating in between those the top and the bottom, the min and the max of those. And also, we could use all of this information to find the range. Notice that if we want to know, well, what's the range of this particular cosine, it would be -2 to 2. It always gets fixated in between its values. But the same point I made before is that the domain is really, it's not going to just be 0 to 4 pi, because that's just the specific when we're looking at one wave, but it will continue moving in both directions because it is a wave function and it's infinite. It will continue to go forever. And so all trigonometric functions have a domain, well, not all, sorry. Sine and cosine have a domain of all real numbers because they don't stop. But typically we don't graph them infinitely, we just graph one period because we know it's going to be repetitive from there. So let's finish up the other examples. In this next one, notice that this one now has plus and minus, meaning it will have a translation as well as a stretch and strength factors. In this one, the amplitude is 1/3, meaning it will be a little bit smaller. Let's go ahead and note that amplitude is equal to 1/3. And then the period is going to be 2 pi over k, which is in this case pi. So here 2 pi over pi, actually pi's will cancel, and that will leave us with just 2. So this is another thing to mention, is that you can make trigonometric functions which have periods that are not weird, because the standard period is pi or 2 pi or whatever, is incrementally based on pi. But if you actually throw pi into a trigonometric function, it normalizes the period to being over unitary numbers, like for example 2. And all that means is the graph is going to be a lot simpler because it's going to finish a complete wave in a more normalized unit of time. So in physics or wherever, when you're studying, if you ever study waves, it's very common to see pi in your trig functions because of that reason. And last but not least, we have a vertical shift of 1. So I'm going to note that too, vertical shift is 1, and that's upwards because it's positive. Remember, on the inside, same direction. Sorry, outside is the same direction, up, down. Inside, opposite direction, left, right. And I don't want to review all that right now because we talked way too much about that in chapter 2. But all transformations work the same always, which is nice to remember with mathematical functions at least. So let's go ahead and graph it from what we know. So another thing I recommend, in the previous ones I did not worry about the equilibrium, but when there is a vertical shift, what I recommend is starting with that, because normally the equilibrium is at 0 for all trigonometric functions, but if it's shifted up 1, that's just going to shift where the equilibrium is going to be, which just means that that's going to be like the centralized point for the up and downness. And since it's sine usually starts at 0, but since if sine starts at 0 and then I add 1, it's now going to start at 1. So basically this graph will start here instead of at 0 because of that. I can imagine the whole thing is being shifted up 1 from where it would normally begin. And then it's going to go through the motion of, well, it's going to go up by the amplitude. So since the amplitude is 1/3, it's going to go up to 4/3. Also, as I always recommend, start with the period before doing anything else. Which is in this case 2. So if I want to graph one cycle, it's going to go to 2, and I could then, put in my quarter points to make sure that I have good outlines for those key points. And this is positive, so it's going to start by going up first. So it's going to go up to the max point of equilibrium. It's going to go up to 4/3. It's going to come back down. Then it's going to go down by 1/3, down to 2/3. So this is going to be, go ahead and label that's 4/3 at the top. Down here, it's going to be at 2/3. And then when I get to the full period, I'm back to the start because it's completed its wave in that amount of time. But basically, this wave is just going to be a lot smaller because of the amplitude. The amplitude controls how tall a wave will be. And the amplitude actually has a lot of interesting effects on waves. Like, say, for example, we're thinking about a sound wave created by a musical instrument or by someone banging on a drum. The amplitude actually affects the loudness, how we perceive the loudness of it, whereas the period actually is related to the frequency, affects the pitch, like whether a note is very high pitched or very low pitched. That was my terrible example of pitch, but all of those things control sound waves, and it's kind of interesting to think about that. The waves are very, very common in our everyday lives, and there's a lot of math that actually goes into them, which is, all of these things connect back to that. And of course, any one of these you could always throw into your calculator to try to understand. Like, say, for example, 1/3 sine pi x plus 1 in this case. Just type it all in. Hit graph. I would usually zoom trig to begin with, just because as I'm messing around with my window, I'm going to be changing the period, changing all that stuff. But zooming trig is just a good starting point, as I recommend. Notice how this one looks very different because, it's a lot shorter because the amplitude made it shorter. It's moved up. It's also vibrating at a different rate because of the period. But, we can notice that you don't really want to rely on your calculator to figure this out, because if I do all that, I can't really understand the graph of the function. So when it comes time for the test, this would be a very likely test question, which is kind of a way that I can check to see, do you understand how all these affect the wave, and then can you make a sketch like this? Whereas if you just copy your calculator, you might be able to figure it out from there, but it's going to be really hard to reverse engineer. And really, all those things are just visible from the equation. You can if you know where to look, it's really that easy. And with the last one, this one has an amplitude of 5, vertical shift of 3, down. Otherwise, it's normal. So this one should be really fast. Might as well just do it. So I would always start with the equilibrium, which is down 3. It's going to have an amplitude of 5, meaning it's going to go all the way up to 2 plus 5, and it's going to go all the way down to by -5, down by -8. But in this example, it kind of highlights too, well, how do I need to make my range, my what value should I use for my y window? But it's all relative to equilibrium, which is always that vertical shift number. That's where I'd begin. And I like to make a dotted line just for an outline. And then sine is going to start at the middle, because sine typically starts at 0 when it's not been transformed. And then it's going to go up to the max, down to equilibrium, down to the min, and come back to equilibrium at the end, which in this case will be at 2 pi, because this one does not have a multiplier in the inside, which is what controls the period. 2 pi over 1, because this is just 1x, k equal 1, is just 2 pi, and it keeps its normal cycle of the unit circle, and we can create, again, a very rough sketch of what this sign looks like, but understanding those key things like amplitude, period, equilibrium, and so on.